Welcome to the Shikasa Boo Motor channel. This channel provides easy-to-understand explanations of car mechanisms. Imagine this. You have to drive several hundred kilometers across a scorching desert. There are no towns or gas stations along the way, not a single one. You're completely on your own. There's no way to even call for roadside assistance. It could just as well be a freezing tundra, or a dense, deep jungle. In such conditions, which car would you choose as your partner? If it gets stuck or breaks down, it could put your life in immediate danger. The Toyota landcruiser would be one of the strongest candidates. Its robustness and reliability translate into exceptional survivability, earning it worldwide recognition. But Toyota has now added a hybrid model to the landcruiser lineup. This is not to say that Toyota's hybrid system is unreliable. However, in extreme conditions, a single failure could threaten the occupant's survival. For the sake of marginal fuel savings and reduced emissions, is Toyota truly willing to compromise safety? The landcruiser lineup consists of 3 models, but their specifications and available engines vary depending on the market. The Type 70 is equipped with a 2.8-liter inline-4 turbo diesel engine, or a 4.0-liter V6 gasoline engine paired with a 6-speed automatic transmission. This model uses a rigid type suspension not only at the rear but also at the front, making it the most capable model for off-road driving. The Type 250 pairs a 2.8-liter inline-4 turbo diesel engine with an 8-speed automatic transmission, while the 2.7-liter inline-4 gasoline engine is mated to a 6-speed automatic transmission. In North America and China, a model is also available featuring a 2.4-liter turbocharged inline-4 paired with an 8-speed automatic and a parallel hybrid system. The Type 300 is the largest landcruiser model, and it is equipped with either a 3.3-liter inline 4-cylinder diesel turbo engine or a 3.4-liter V6 gasoline turbo engine, both paired with a 10-speed automatic transmission. A model that adds a hybrid system to the 3.4-liter gasoline engine and 10-speed automatic transmission combination has been introduced in the Middle East, and it has also been announced that it will be launched in Eastern Europe starting in January 2026. This system is also installed in the Lexus LX700H and has been introduced in Asia, including Japan, as well as in North America. The same system is also employed in the North American Sequoia and Tundra. Let's take a look at the powertrain configuration of the Type 300 hybrid. The engine is a 3.4-liter V6 gasoline turbocharged unit. A hydraulically controlled multiplate clutch is located behind the engine, enabling the engine to be disengaged from the powertrain. The electric motor performs 3 functions. It propels the vehicle, starts the engine, and operates as a generator. The output from the motor is transmitted to the torque converter. The transmission is a 10-speed planetary gear type. A low-range reduction gear set is mounted at the rear of the transmission. A Type C torsion center differential is positioned behind it. Part of the output from the center differential is transmitted to the rear differential, while the remainder is delivered to the front differential via a chain and sprockets. Now, let's examine the relationship between the engine, the clutch, and the motor. The clutch outer housing is connected to the engine's crankshaft. The clutch inner hub is connected to the motor rotor. A series of clutch plates are stacked between the outer housing and the inner hub. The motor rotor transmits its output to the torque converter. When the clutch is disengaged, the engine's rotation is not transmitted to the motor or the torque converter. Conversely, even when the engine is not operating, the motor can transmit its output to the torque converter. Next, let's examine the operating principle of a planetary gear type low-range reduction gear set. The ring gear is fixed to the transfer case. The output from the transmission is fed into the sun gear, and the drive is delivered from the planetary carrier to the center differential. An electric locking device is provided between the sun gear shaft and the planetary carrier shaft. In 4-high mode, the sun gear and the planetary carrier are locked together by the locking device. Because the sun gear and the planetary carrier rotate as a single unit, the input speed is transmitted without any gear reduction. When the driver selects 4-low mode using the transfer switch, the locking device is released by the electric actuator. The input rotation is reduced and then transmitted as output. Next, we will examine the operating principle of a Type C torsion center differential. This differential is of the planetary gear type and features an uneven front-to-rear torque distribution function. First, the operating principle will be explained. Engine torque is input to the planetary carrier and is transmitted from the sun gear to the front differential and from the ring gear to the rear differential. Now, let's consider the case where the sun gear is held stationary. The ring gear has 60 teeth, and the sun gear has 24 teeth. If the input rotational speed is set to 1, the ring gear speed output to the rear wheels is increased to 1.4, while the sun gear speed is 0 because it is held stationary. Because speed and torque transmitted through gears are inversely related, when the speed increases by a factor of 1.4, the torque is reduced to approximately 0.7 times. This means that a torque of approximately 0.3 of the input torque is required to lock the planetary carrier. In other words, this differential transmits 70% of the input torque to the rear wheels and 30% to the front wheels. The torque distribution ratio can be determined by the tooth counts of the planetary gear set. In the case of the landcruiser Type 300, 60% of the torque is distributed to the rear wheels and 40% to the front wheels. Next, let's take a look at the limited slip function. Its key features are the use of helical gears for the planetary pinions, and the fact that the planetary pinion shafts are not fixed to the planetary carrier. The planetary carrier transmits torque by applying force to the sides of the planetary pinions. When the front and rear wheel torques are equal, the planetary pinions do not rotate, so the differential operates in the same way as an open differential. To illustrate the torque difference between the front and rear axles, the planetary carrier is fixed, and the ring gear and the sun gear are rotated in opposite directions. When a torque difference arises between the front and rear wheels, the planetary pinions tend to rotate. But friction at the contact interface between the planetary pinion sides and the planetary carrier produces a force that opposes this rotation. In addition, because the planetary pinions are helical gears, axial forces are generated along the gear axis during rotation. This force presses the planetary pinions against the side faces of the ring gear, generating friction, which also resists the rotation of the planetary pinions. As a result, when a torque difference occurs, torque is transferred from the slipping axle to the non-slipping axle. Depending on the market, the rear differential can be equipped with either a Type B torsion differential or an electronically controlled differential lock, while an electronically controlled differential lock can be selected for the front differential. We will explore the survivability of hybrid vehicles in the desert. This animation shows the power flow of the parallel hybrid system used in the Land Cruiser. When the vehicle is stopped, the engine is off and the clutch is disengaged. During launch and low-speed driving, the electric motor propels the vehicle using power supplied by the hybrid battery. Once the vehicle speed exceeds a certain threshold, the clutch engages and the electric motor starts the engine. In other words, at this moment the electric motor operates as a traction motor, while simultaneously functioning as a starter motor. Once the engine is running, it takes over as the primary power source. When strong torque is required, such as during hard acceleration or crawling, the electric motor assists the engine. What would happen if the hybrid system were to fail? Naturally, launch and low-speed driving using the electric motor would no longer be possible. If the electric motor, which also functions as a starter motor, does not operate, the engine cannot be started either. That means, Even if there are no problems with the 12-volt electrical system or the engine, the vehicle will be unable to move if the hybrid system fails. To address this, Toyota added a 12-volt starter motor and alternator, components that would normally be unnecessary in a hybrid system, as well as an electric oil pump. This allows the engine to be started, and the hydraulic pressure generated by the electric oil pump engages the clutch, transmitting the engine's output to the transmission. With this setup, even if the hybrid system were to fail in the middle of a desert, the Land Cruiser would still be able to carry you safely to your destination. However, once an error message appears on the meter display, the decision to turn back or continue forward is up to you. Although no official announcement from Toyota could be found, several sources indicate that the 2025 North American Type 250 Land Cruiser has been equipped with both a backup starter motor and an alternator. You might say, then why not equip other hybrid vehicles with a backup starter motor as well? Let's consider a power split hybrid system, such as those used in the Toyota RAV4 and the Ford Escape. This system consists of an engine, a planetary gear-type power split device, MG1, which primarily functions as a generator and starter, and MG2, which primarily operates as a traction motor. MG1 starts the engine by functioning as a starter motor. During engine-driven operation, MG1 functions as a generator, while simultaneously applying reaction torque to the sun gear of the planetary gear set, thereby directing the engine's torque to the wheels. Even if a backup starter motor were equipped to start the engine, if MG1 were unable to generate reaction torque due to a hybrid system failure, the planetary gear set would simply spin freely, preventing the engine's torque from being transmitted to the wheels. In other words, the vehicle would be completely immobilized. How about a series parallel hybrid system, such as the one used in the Honda CR-V? During normal driving, the engine functions solely to power the generator and does not directly drive the wheels. For this reason, if the hybrid system fails, the vehicle cannot move at all, even if the engine could be started by the backup starter motor. This system also features an engine direct drive mode. In this mode, the vehicle can theoretically drive as long as the engine is running. The CR-V employs a 2-speed direct drive setup. The high gear ratio of 0.708 comparable to a typical top gear, and a low gear ratio of 1.409, which is roughly equivalent to the 3rd to 5th gear range in a conventional transmission. With ratios like these, it would be nearly impossible to get the vehicle out if it were stuck in deep mud. If you would like to learn more about these hybrid systems, please watch these videos. The links are provided in the description. As such, the Land Cruiser Hybrid offers outstanding off-road capability, while maintaining the same high level of survivability as the internal combustion engine model. Whether your mission is pure adventure, a natural resources venture, or the discovery of new species, you can set out with total confidence. One question remains. If Toyota went through the trouble of adding a backup starter, are they secretly worried about their hybrid reliability? Let's leave that aside for now. Thank you for watching. If you enjoyed this video, please consider subscribing to the channel. We'll see you in the next video.